Acids and bases. There are essentially there are two theories about acids and bases here. There are actually three. And in chronological order, the Arrhenius concept came first. And what Arrhenius said was that acids are any compound that has a proton or a hydrogen that can be dissociated from the molecule. And when it does that, it produces these two species. And for the Arrhenius situation, we're in aqueous solution. This one has limited application. And I think, yeah, we're going to talk about those in a minute. The base in the Arrhenius concept is some sort of part of the molecule, and it has to have a hydroxyl group with it. This is the polyatomic ion OH minus when it separates. And then what that produces is this set of species in aqueous solution. Okay, that's Arrhenius concept. And for a vast majority of the situations, this works fine. But there was a problem. Arrhenius came first, and then acid and base solutions were recognized in different situations that didn't follow this scenario. And actually, this is the troublesome one. In other words, if you dissolve ammonia in water, you get a basic solution, but it doesn't have an OH group in it. So we had to figure out, how is that possible? And two scientists independently came up with the proposal. Bronsted and Lowry said that what happens is, in this situation and in many others, when you don't have a OH there, but you get a basic solution, there's a reaction with the water molecule. And what happens is one of these hydrogens is transferred to that ammonia and makes the ammonium ion. And what's left? Well, if you take away one hydrogen, you have an OH left over. That's where the basic character comes from. So Bronsted and Lowry proposed that an acid donates a proton or a hydrogen ion, and a base accepts a hydrogen ion. That solves the problem, because now this is a base. It accepts a proton from water. And notice with that definition, this is the base because it accepts the proton, and water is an acid because it donates a proton. All right. Okay. The other possibility, of course, is if we take an example of an Arrhenius acid like that, and we react it with water, then we transfer a proton from hydrogen chloride or hydrochloric acid. This proton is over there, and now we have chloride ion in an aqueous solution plus this polyatomic ion, a hydronium ion. That makes this the acid because it donated, and this is the base because it received. Now, I might as well go ahead with terminology here. This acid when it donates a proton, now it becomes the conjugate base. It's the conjugate base of this acid. And this water, it acts as a base. It accepts a proton and it produces a conjugate acid. And that's because this could conceivably accept a proton, right, making it a base. This could donate a proton, making it an acid. I think there's a separate slide on that here coming up. Let's see. Well, this is a like animated version of this process. The water molecule is the red and the blue is the ammonia. And there's a tug of war between those two to take a proton from one and give it to the other. But you can also do this with water, right? If you have pure water and two water molecules encounter one another, then one of them can act as the acid and the other can act as the base, transferring a proton to the other one. Right? And take your pick, right? We can't tell the difference. Let's just say, for argument's sake, this is the acid and this is the base. So this will donate a proton to this molecule. That makes this a conjugate base, makes this the conjugate acid. This reaction does occur in pure water. One water molecule acts as an acid, the other acts as a base. And there it is in black and white and red and purple. Okay, now we need definitions. We need a chemical definition for strength of an acid or a base. We're going to take acids first. When a chemist says an acid is a strong acid, what he or she means refers to the dissociation of the molecule. Right? We do it like this, of course, we're going to have A minus plus the hydrogen. What strong acid means in chemical terms is the equilibrium is way, way to the right. Okay, so we studied in our equilibrium chapter that the K for this value would be much, much, much greater than 1. Right? That would send the equilibrium over largely to the product side. When we say weak acid, that means the K is less than 1, much less than 1. And that would favor the reactant side. That's the chemical definition of strong acid versus weak acid. Now, one thing we also observe is if this is a strong acid, it produces a weak conjugate base. So a strong acid wants to dissociate completely to that direction. That means once you produce this base, it doesn't want to go back. It doesn't want a proton. So that's why this is strong and that's weak. And vice versa. If this is a weak acid, then it will produce a strong base, which means it really wants a proton. And where does it get a proton? Well, if you add this species in aqueous solution, independent of this reaction, in other words, you take that species right there and add it into water, then what it's going to do, if it's a strong base, it's going to go for a proton on that water. So how would you do that? Well, if this is acid, then in order to introduce this one, you need a counter cation. So we would say something like maybe sodium A minus. Or if we use a real example, we could use, let's see, sodium acetate. Okay. Sodium's not going to react with water, but this acetate will, and it'll take a proton from that molecule and produce, let's see, it'll produce acetic acid plus a hydroxyl. Okay. So if it starts off as a weak acid, it produces a strong base, and a strong base means it's going to snatch a proton from that water molecule. And that makes the basic solution. We'll talk about that a little bit more in detail in just a few minutes. This is just an artist's rendition of what you should expect. With a strong acid on the left, the reaction is essentially complete to the right. And if it's a weak, okay, they're using a B here for instead of an A for the right-hand side to designate a weak acid. So that would largely be the undissociated acid. In other words, this is a weak acid, acetic acid, right? Vinegar. It's a weak acid. It's not going to dissociate very much. So if it's weak here, it produces a strong base, the acetate ion. That makes acetate a strong base. Okay. I referenced these earlier. If the acid is strong, the K is going to be very large. And if the acid is weak, K is going to be very small. And it's measurable, right? In fact, next week's lab, you're going to determine the Ka for acetic acid. No mystery. We're going to use a pH meter. Okay, so here is the concept we call autoionization or self-ionization of water. Now, this also happens with other molecules, and the example there is ammonia. But if we look at water, one water molecule behaves as an acid, the other as a base, produces a hydronium ion and a hydroxyl ion as a consequence. Doesn't produce very many of them, right? Because both water and water are weak. In other words, one doesn't want to give up a proton, the other one doesn't want to accept a proton to a limited extent. So what we get is everything is largely to the left. It's still mostly water, but there are a few, very small number of hydronium ions and hydroxyl ions in pure water. The same thing can happen with the ammonia. You have pure ammonia. That's a difficult concept, I guess, but it's possible. Pure ammonia. Farmers use it. Large, say for instance, large corn farmers use pure ammonia. We call it anhydrous ammonia to get nitrogen to their crops. And it takes some special equipment, stainless steel. Everything has to be stainless steel, but they inject it into the ground, because if you just blow it out the nozzle, it won't land on the ground. It'll turn to a gas like that, just gone. So you inject it into the ground where it combines with water and does that reaction I mentioned earlier. It also produces, just as a side note, it produces a kill zone like that. Like everything is dead. So it takes a while for microbes and roots and things to re-invade that area. Anyway, inside that tank of pure ammonia, you get this reaction where you have this ammonia molecule and this ammonia molecule reacting. One's an acid, one's a base. One produces this, and the other produces Yeah, and the other produces things. So this autoionization happens with many different molecules. These are two examples. The most important one for us is water. This is also known as amphoteric behavior. What it means, ampho means either or. And water, that means water can act as an acid or a base. Now, when we write out the equation, and you'll see it, this is actually the chemistry that happens. You get this hydronium ion plus the hydroxyl. That's the chemistry. But for calculation purposes and for ease of management, oftentimes it's written this way. Okay. And the calculations are exactly the same either way you do it. This is the chemistry. This is convenience. This is an abbreviated form. And when we write it this way, if you write the equilibrium constant for this, the expression for the equilibrium constant, we give it a special subscript, Kw. I mentioned that in chapter 13. Well, water is a pure liquid, right? So it's not part of the calculation. Solids and pure liquids don't enter the equilibrium expression. So all you have is hydrogen ion concentration and hydroxyl ion concentration at equilibrium. And when we measure those values at, I think it's 25 degrees, we get 10 to the minus 7th molar here. And this one has to be what? Exactly the same, right? Because you're dissociating that molecule. If you end up with 10 to the minus 7th here, you also end up with 10 to the minus 7th there. And that's molar. That's what the square brackets mean, remember? And then if you multiply those together, you get 1 times 10 to the minus 14. Right? That is the equilibrium constant for pure water at 25 degrees. And I might add, no matter what else is going on in water, whatever else you add to water, acids, bases, salts, doesn't matter. This reaction is also always occurring, even when you add all that other stuff to it. Now, whether or not it's significant depends on what you add and how much you add. So there's a competition going on there for the proton movements. Okay, we have 3 possible situations when we consider the balance of hydrogen ions and hydroxyl ions in water. One, the easy one, is pure water. Pure water will give you a balance of equality. Hydrogen ion and hydroxyl ions are exactly equal in concentration. In that case, we have a neutral solution. And this neutrality is in terms of acid-base. The next possibility is if we add acid to aqueous solution, to pure water, add an acid, we will increase the hydrogen ion concentration, and it will exceed hydroxyl ion concentration. That's an acidic solution. And then, of course, we can go the other direction. We can add a base like sodium hydroxide, like liquid plumber. And in that case, you'll have an excess of hydroxyl ions. There'll be higher concentration here than there. And this will be our basic solution. All right. I mentioned this earlier. The equilibrium expression for, say, this situation where we add an acid to water, then we get this reaction. And we're going to use the abbreviated form. That's the complete form. That's the chemistry right there in that slide. That's what happens. But this, for calculation purposes, is more convenient. So we write it this way. Oops. My mistake. Here we go. And the Ka, which is the equilibrium constant for the acid, would now be the concentration of hydrogen ions, concentration of the conjugate base divided by the undissociated acid. And these are all in aqueous solution. They have to be solutions. Otherwise, we won't introduce them into the equation. So that's the Ka expression for this acid. All right, that's the true, that's the chemistry that's happening right there. This is the one that you'll see more often because it's more convenient to write it that way. So if the equilibrium lies to the right, the value of Ka should be what? It should be heavy in this amount. It should be large. Right. And if the Ka is small, it should be favoring the reactants, which would make it a weak acid. All right. Now, while we're here, let's just write the Kb expression for this reaction. If we have a base and it's an aqueous solution and it's going to dissociate and produce a B plus and an OH minus. Yep, that works. Then the Kb would be equal to this conjugate acid. Yeah, that works. That would be the Kb for this expression. Now, if we have this acid, and say it's a weak acid, and it produces a strong base, strong conjugate base, then we can compare this value, this Ka, to the Kw for water and see which one is dominant. If the Ka for this one is larger than 10 to the minus 14 by a significant amount, say a couple of orders of magnitude at least, then the Ka is dominant and we don't have to consider the Kw because it's virtually swamped by this expression. Okay. So I'm gonna have to make some room now. All right. So let's say we have a 1 molar solution of HCl, which would be hydrochloric acid. Let's put these in order of strongest to weakest base. So if we have hydrochloric acid, aqueous, and it produces these two species in aqueous solution, of course. This is a strong acid, very strong acid. This is a very weak base. Okay. The other possibility is another acid, a weak acid. And it produces hydrogen ions plus this species. If this is a weak acid, this makes it a strong base. Okay? And then we have the situation where we're looking at water. And these are all aqueous, of course. That's pure liquid. Okay. We want to compare this species, right, according to that chart, this species, and this one. Put them in order of strongest to weakest base. All right. So a strong base has a very, very strong affinity for hydrogen ions. Okay? If this one is already over here, it's not looking for more hydrogen ions. This one's not looking for any hydrogen ions at all because it's a very weak base. So it's going to be the weakest. The strongest base is going to be this one. And then water's in the middle. Based upon the strength of the acid producing those bases. Of course, this one we consider independently because we're not talking about its products. We're only talking about the water molecule. Since the water molecule doesn't go very far that direction, then that makes this a weak base. Excuse me, strong. A weak base, but not as weak as this one. Okay, let's see if I got it right. It didn't say. Okay, well, you have to take my word for it. Oh, no, we're going to talk about it some more. Excuse me. How good is chloride as a base? Not good at all. Is A minus a good base? Yes, very good base because it came from a weak acid. There we go. All right, consider a solution of sodium A. And we did sort of look at one of those before when I was trying to explain how you get that A minus in solution if it's a strong base, strong conjugate base. And you do it by combining it with some cation. Right? Then it would completely, remember, all sodium salts are soluble. So we're going to produce this sodium, which reacts with nothing, and this A minus, which is a strong base. Okay. So now that in solution combines with water and produces, and produces the conjugate acid HA plus the conjugate base OH minus. So the equilibrium should lie far to the, consider the solution. A minus is the anion from a weak acid. No, that's not right. That's wrong. Should be to the right. Because A minus comes from a weak acid, making it a strong conjugate base. Now, if A minus is an anion from a weak acid, oh, okay. We're in the same scenario, a weak acid. Now the question is, what's the value of Kb? Is Kb greater than or less than 1? Well, if we look at the Kb as oops, sorry, my mistake. That's not the equation. This is the equation. Now, this equation, if this is a strong base, we would expect the equilibrium to be to the right. So the expression for the KB for this one would be HA OH minus divided by A minus. Because water is a pure liquid, it's not part of the expression. So that value being far to the right, KB would be greater than 1, right? And that's wrong. It's not less than 1, it's greater than 1. Okay, does this mean A minus is a strong or a weak base? Well, it means it's a strong base. All right. So acetic acid is a good example to work with as a weak acid. But hydrogen cyanide is also a weak acid. The difference is that acetic acid is stronger than hydrocyanic acid. So if we try to arrange these in order of weakest to strongest bases, we have what? Well, we have our original that we looked at earlier. That makes this a very weak base. Very weak base, because that's a strong acid. Okay, so we're looking at this species right here in that group. Then, of course, we still got the water. Right? And then we have hydrocyanic acid. These are all aqueous. And then we have acetic acid. Which dissociates like this. Okay. We're looking at this one. And we're looking at, yes, this one. And we want to put them in order of weakest to strongest base. Okay. First, let's compare these two. This is a stronger acid than that one. That's what it says. Acetic acid is stronger than that one. That means if this is a stronger acid than that one, it produces a weaker base. Right? So this is the strongest base. This is the next strongest base. That's the weakest one, and water would be next to that one. So from weakest to strongest, weakest would be this one. Then water. Then the next one would be acetate. And cyanide ion. That's the order of weakest to strongest. Okay. It didn't say. Oh, talking about it again. All right. Well, if you actually have numbers to go with it, the K for water, right? KW is 10 to the minus 14. The Ka for this acid, hydrocyanic acid, is 10 to the minus 10. 6.2 times 10 to the minus 10. And acetic acid, the Ka is 1.8, I think, times 10 to the minus 4. 5, excuse me. 5. There we go. And then this one has the Ka is essentially infinity. Put an equal sign. All right, so in this case, if you look at these values, then you find that if we were talking about this species right here, this would be the strongest base. But we're not, we're talking about this one. And so this tells us that it wants to be this side. It doesn't want a proton from anybody. Not quite as repulsive as the chloride ion, but still. And this being the weaker of the acids produces the strongest base. So then our order is chloride, water, acetate, and cyanide. All right, that was a discussion of comparisons of conjugate bases. But a great many reactions are combining these species. And here's one example where we have hydrocyanic acid and fluoride ion in the same solution. So we want to see, do we think that the K value for this reaction is greater than 1, less than 1, or equal to 1? All right. So let me see if we're going to have a discussion. Yeah, we're going to have a discussion. So we're given the Ka for hydrocyanic acid is, again, 10 to the minus 10. The Ka for hydrofluoric acid is 7.2 times 10 to the minus 4, which means it is a stronger acid than acetic acid. Acetic was 10 to the minus 5, which doesn't matter for our purposes, just pointing that out. All right. So if we take this reaction and we look at what each of the Ka's mean. The Ka for HCN is very small, strongly driven to remain as HCN. HF is small, it wants to remain as HF. The question is, which one wins? Well, a hydrocyanic acid is much, much weaker. It wants to stay HCN more than HF wants to remain HF, which is on the right-hand side. So if we compare the left-hand side here, CN, and then HF on this side of the equation, which side wins? Well, you look at the Kas. The HCN is so small, it doesn't want to go that way by an order by 10 to the minus 10. Whereas HF wants to stay this side by 10 to the minus 4. Right? This one has a much stronger impulse to stay as HCN. So the reaction is going to be to the left. Right? So if we write the expression, then, and we know that if it stays to the left, that means the K would have to be less than 1, correct? Because it's on the product side, the reactant side. Reactant side favors K less than 1. Yeah, because this side is going to be in the numerator, it's going to be very small. This side in the denominator, very large. So that gives you a K less than 1. Now that's a semi-quantitative or qualitative approach to reason out which side it's going to be on. But you can also determine what the actual K is for that reaction. And we're not going to do it yet. What we're going to look at now is the relationship of Ka and Kb. If you have the Ka for a reaction, we want to be able to calculate the Kb for its conjugate base. Right? So if we have this reaction which produces A minus plus A plus, we have a Ka expression for this one of A minus and H plus and HA in the denominator. What we want to know is, what's the Kb? Well, the Kb has to be focused on that species right there. Right? You can get an inverse, right? We know how to do the inverse of Ka, right? We just flip that. But that's not what we're looking for. The Kb means that we take this species and combine it with water and we get the acid back plus the OH minus. So the KB actually looks like this. Right? And that is not the inverse of this one. This is a completely different reaction. But they are related, and we can calculate one from the other. And here's how we determine it. There's the Ka expression. Right? This is the KB version that I've written there. Now, what if we combine those two reactions? Right? We know how to do that. We've done Hess's law, right? We know how to combine equations, and we used it in the equilibrium expressions also. So if we combine those two, that means if we add the top one to the bottom one, HA's cancel, A minuses cancel, and what do we end up with? We end up with water. And if we combine the two equations, how do we do that when we're in equilibrium? The Ka's must be multiplied. So it's Ka times Kb, which happens to be, if we cancel the, well, let's see. That would be A minus H plus times HA times OH minus, correct? Right, we just multiply these two together. So Ka times Kb is actually this expression. And in the denominator, we have HA and A minus, correct? Okay, now cancel things, right? Just, this is math. That one cancels. This one cancels. And we're left with H plus and OH minus. Okay, which we know to be 10 to the minus 14, or KW. All right. So if we solve for KB, then KB is equal to Ka on the other side is KW divided by Ka. That's how you find KB. You divide the Ka into KW, which is 10 to the minus 14. All right, now to calculate the value of K for this reaction, we're not talking, we have to shift gears here again. We're not talking about going from Ka to Kb. We're actually we're talking about combining two equations with their respective K values. All right, so that's where we're headed. We're going to break this reaction into two reactions. Hydrocyanic acid produces that reaction. HF produces that reaction, but we need the reverse of HF, right? Because HF is on the wrong side. So there's HCN and there's HF, but HF needs to be reversed. Right? So we reverse the reaction, which means the K value has to be inverted also. Right, so there's your K inverted HF. Now we'll go to the next page. And when we combine those two, we have to multiply the inverted HF and the former HCN, and we get 8.6 times 10 to the minus 7. That confirms what we determined to be the direction of the reaction. We said the reaction should be favoring reactants, be less than 1. And there it is. In fact, much, much less than 1, 10 to the minus 7. All right, now let's talk about pH. You ever seen pH before? You guys probably have, right? If you're phlebotomists. So you know what acidosis would look like. as far as blood pH would go, right? What's normal pH for a blood plasma? Very narrow range, right? Is that right? Did I get that right? I think I did. Don't remember? Well, we're going to define pH in chemical terms now. There was a scientist. Let's see, is he on another slide? Oh, we left his name off. That's a pity. His name was Sorensen. I think he was Swedish. He was working with systems that were within a relatively narrow range of hydrogen ion concentrations. But he wanted a convenient way to express those values rather than scientific notation of hydrogen ion concentrations, which would be unwieldy. So he came up with this mathematical conversion of hydrogen ion concentrations. He says, why don't we take the log of it? Right? Take the log of the hydrogen ion concentration. Well, you know, for example, if we were neutral, 10 to the minus 7th molar hydrogen ion would give you what? Right? Base 10, the log of this value to the base 10 is the power of 10 that gives you that number. So the power of 10 that gives you that number is minus 7. Right? That's how you interpret a logarithm. Well, he didn't want negative numbers either. So he said, okay, I'll just stick a negative out here. So that means the pH of the hydrogen ion concentration, if it's 10 to the minus 7, would be this expression. And that's a mathematical expression. You can stick any value you want to hydrogen ion concentration in there and calculate the pH. It could be negative. Yeah, it could. It's most likely positive in the range we're going to use it, but there's no reason it can't be negative, right? What if you say hydrogen ion concentration is 10 to the second power? Right? It's 10 to the second, 100 molar. That's kind of ridiculous. Let's say 1 molar. Okay. 10 molar, excuse me, 10 molar. Then the pH of this one will be minus 1. Right, so minus pHs are possible. They're just not very useful. Okay. Also, when it's a mathematical fact, if we're looking at significant figures, say your hydrogen ion concentration has, let's say 1.00 times 10 to the minus 7 molar. 3 significant figures. The pH calculated from that is going to have 3 decimal places. Right, so they have 7.000. And if you go backwards, of course, 3 decimal places, if you go back from pH to hydrogen ion concentration, now you're going to have 3 significant figures. All right. Okay. So if we have a neutral solution where the hydrogen ions are equal to the hydroxyl ions, we have a concentration of hydrogen ions at 10 to the minus 7th molar. We showed that earlier. So that means the pH would be 7. If it's basic, then the hydrogen ion concentration would be less than the hydroxyls. And remember, Kw equals, this is always happening in solution, 10 to the minus 14. So if this is greater, if hydroxyls are greater than hydrogens, let's say, for example, instead of 10 to the 7th, it's 10 to the 6th, which would be an increase, right? That's bigger than 10 to the minus 7. Well, this one would have to be 10 to the minus 8 in order to give you that value. Right? Just add them up. That's how you do it. Well, what would the pH be then? Well, the pH is negative log of 10 to the minus 8 equals 8. Okay, so for basic solutions, the pH is greater than 7. For acidic solutions, the pH is less than 7. Right? If we made this one minus 8 and this one minus 6, then the pH would be 6. So you go into the smaller numbers. The smaller numbers of pH are more acidic, or the acidic range. And there's some examples. We don't have time to stop there. Okay. So this is a mathematical transformation. Right? There's nothing mysterious about it. If we have 1 times 10 to the minus 4th hydrogen ion concentration, then the pH would be negative log of 10 to the minus 4, which would be 4. Okay. The OH, if we want to give pH for OH, this takes a little more doing. 0.040 molar hydroxide. Right? So if that's the hydroxide concentration times the hydrogen ion concentration equals 10 to the minus 14, right? This is Kw. Hydroxide times hydrogen. Then we can calculate the hydrogen ion concentration and then determine the pH. So hydrogen ions would be 10 to the minus 14 divided by 0.04, which will be hydrogen ion concentration equals 2.5. Let's see, 2 significant figures. That's all we need. Times 10 to the minus 13. So if we take the negative log of that, the negative log of this, right, what do we get? Well, I'll just take the log and change the sign. I get 12.6 pH. Okay? So that tells us this solution is basic. It's much, much greater than 7. Okay? I'll leave that one up there while we do this next one. If the pH of the solution, pH equals 5.85, then we want to know what's the hydrogen ion concentration. Well, the pH is equal to the negative log of the hydrogen ion concentration. Now, so how do you deal with that? Well, remember what a log is. Log base 10 of x equals y. That means x is equal to the power of 10, that is y. Okay, remember that from math class? That means if we know what this one is right here, then we need 10 to that power, except we've got this negative on that side. We can't leave that negative over there. So we got to move the negative back over here. 5.85 equals log of hydrogen concentration. Now we can do 10 to the minus 5.85 equals, not the log of, actually equals hydrogen ion concentration. Right, so where do you find that in your calculator? Well, look for the key that says log. Then look above it, which would be a function change. Should say 10 to the x. Okay, that is what we've done here. So if I put in 5.85, change sign, and then I say 10 to the x, I get, let's see, 2 decimals means I can have 2 significant figures. 1.4 times 10 to the minus 6 molar. Okay? That's how it's done. And it's purely mathematical. We're just dealing with logarithms. We could do this in math class. And you wouldn't even know. We wouldn't even have to tell you it's chemistry. We'd just say, right, solve that equation. That's what you would do. Now, remember this. I assume everybody's got this one done already. Remember that example before, 0.040 molar hydroxyls. We wanted to find out what's the pH. Well, we went through it and did it the hard way. I'm going to show you the easy way now. We start off with KW equals this times this, correct? Let's take the negative log of both sides. Actually, let's take the negative log of the whole thing. Right? If we take the negative log of everything inside those brackets, we get negative log of KW is PKW. All right? We know the negative log of this one is pH. Then the negative log of this one is POH. But what happened to that multiplier? Right. When we take a log of A times B, it's the same as the log of A plus the log of B. So this becomes a plus sign. Right? More math. Sorry, can't be helped. What's the negative log of this value? 14. The negative log of 10 to the minus 14 is 14. So notice PKW equals pH plus POH, which is equal to 14. And that's what this sequence is showing us. All right. Now, if we're neutral, pH is 7, POH is 7, and 7 plus 7 is 14. If, let's see, our previous examples say, if pH is 8, POH would be 6 to equal 14. So what we could have done with 0.040 molar hydroxyl ion concentration is take the negative log of that value. Let's just do that. 0.040 negative log is 1.4. You got two significant figures, actually 40. 40 equals POH. That means pH equals 14 minus POH, which is 1.40, which is equal to 12.6. Okay. So we got the same answer. It was just a little easier to do it this way. Let's see. All right, we did that. Let's see. POH for each of the following. We did this one. POH for that first one, for the second one is 1.4. Right. There it is, 1.4. POH for the top one, where we're given the hydrogen ion concentration, we just do the pH. What's the pH of 1 times 10 to the minus 4? It's 4, right? pH of 4? Yeah, negative log of 10 to the minus 4 is 4. And then subtract that from 14, that's 10 POH. This is pH, this is KW, this is POH. All right. Oh, yeah, we did that one right here. Right there. Okay, and I already did this one on the board. Oops. Did I do that? I didn't do that one before. Sorry. I didn't want to like it. So let's make a little room. The pH of a solution is 5.85. What's the hydroxyl ion concentration for this solution? No, that's not right. Calculate the pOH first. No, calculate the OH minus. Oh, yes. Okay, I'm sorry. No, that's right. That's right. If pH is 5.85 and subtract it from 14, that will give you pH. This is pOH. No, it's pH. Sorry. Oh, I'm getting confused. This is OH. Now, okay. And this should be let's see, 5, 1, and 5. 13 is 8, 8.15, right? So now if this is pOH, then hydroxyl ion concentration is equal to 10 to the minus 8.15. Which is 2 decimal places. 7.0 times 10 to the minus 9 molar. Oops, 7.1. That's my mistake. I rounded the wrong direction. There we go. All right. So when we've got acid-base problems to deal with, you need a strategy to solve them. You look at what's given to you and say, what are the major species that are in solution? Then you look at what reactions can those species undergo? What are reasonable reactions? And as you're doing that, ask yourself, is this an equilibrium reaction where you have a balance between the reactants and products, or is it essentially go to completion? Right, like strong acids, strong bases, they'll go to completion. And then you eliminate the ones that don't make any sense or the ones that are out-competed. Then you solve for the pH. So we need an example. Let's see. We have an aqueous solution of 2 times 10 to the minus third molar HCl. What are the major species in this solution? Well, let's see. You have HCl, which dissociates completely, right? It's a strong acid. So there's no HCl left. It's all hydrogen ions, chloride ions, and there's water. Remember, this is aqueous solution. There's always H2O there, right? So we say, who's competing, right? Does it matter that water dissociates into H pluses and OH minuses? No, because they don't make that much. And at this concentration, 10 to the minus third molar, the dominant species there that controls the pH is the hydrogen ions produced by the hydrogen chloride in solution. So you can safely say that the hydrogen ion concentration in this solution is 2 times 10 to the minus third molar. Then we can calculate the pH, which is 2.7. Now, what if we calculate the pH of 1.5 times 10 to the minus 11th molar HCl? Right. This would dissociate and produce 1.5 times 10 to the minus 11 molar hydrogen ions. But we've got another reaction in there where water molecules dissociate to produce H plus and OH minus, right? Okay. If this were pure water and this reaction is going on all the time, how much of that is produced? 10 to the minus 7th molar, right? 10 to the minus 7th molar. Right? What impact does this have on that? This is 4 orders of magnitude weaker than that. That means this dominates the pH. And this solution is still neutral. Why did it say 10.8? Oh. I think that's an error. Yeah, if you just take the negative log of that value, that gives you 10.8, but you've still got water producing this much. I think that's a mistake. I mean, that's correct calculation. The math is correct, but the chemistry is not. Does everybody see my logic there? This reaction is competing with that reaction. This one produces 10 to the minus 7th molar hydrogen ions. This one only produces 10 to the minus 11th hydrogen ions. This one outcompetes it. That's an error. I need to correct that slide.
So the only difference with the example before this one, I guess, your logic is because the molar for HCl is higher.
Yes. Molar concentration of hydrogen ions in the first example were much, much higher than this value. So it dominates. Let's see what it was. 10 to the minus 3 is much, much more than 10 to the minus 7 by 4 orders of magnitude. Right. So this one has very little impact on the pH. Whereas in this scenario, let me think about this a minute. Let's go back to the one that I thought was wrong. If that were worded differently, then that calculation would be correct. If we measured the hydrogen ion concentration, no, that's not right. You can't say a solution of hydrochloric acid at that concentration would give you a pH 10.8. Only if you could say the hydrogen ion concentration was measured as 1.5 times 10 to the minus 11th. And don't put the HCl in there. In that case, then you would have to have added base to decrease the hydrogen ion concentration to that level. See what I'm getting at? If you just focus on the HCl, that's a strong acid, and that concentration of HCl doesn't have the ability to overcome this concentration of hydrogen ions from the water. But if we eliminate this part and say, we measured the concentration of hydrogen ions to be that, then the pH would be 10.8. But we couldn't get it by adding hydrogen chloride to the solution. That's impossible. You have to add a base to get to that basic pH. 10.8 is base, right? So that's the problem with this slide. Does that make any sense? Yes, no, maybe? We need more practice. All right, moving on. When nitric acid is added to water, a reaction takes place immediately. Right? It's a strong acid, so it's going to be essentially all the way to the right. Why is this reaction not likely? Because nitric acid is a strong acid. That means NO3 minus is a very, very weak base. It does not take a proton from water. It doesn't want one. So that reaction is not valid. This is a competing reaction in aqueous solution. But even though this reaction is always taking place, water is the major contributor. Right? Water is still the major component there. Let's see. So if we have a solution of nitric acid is 10 to the minus 2 molar, that is, it would produce 10 to the minus 2 molar hydrogen ions versus 10 to the minus 7th for the water reaction. This concentration of nitric acid dominates, and we can calculate the pH based upon that concentration only. Right? They're major species, and if we calculate the negative log 1.5 times 10 to the minus 2 molar hydrogen ions, we get 1.82 pH. That would be an accurate measure. We could measure this pH of the solution, and it would come out very close within experimental error of 1.82. All right, so these are just steps that you would follow to solve a weak acid equilibrium problem, right? We've been talking about strong acids at this point. Now we're going to look at weak acid equilibrium. In this case, we do have to consider all the species that are produced in the solution and which is the dominant reaction. So you list your major species, you choose the ones that can produce hydrogen ions, write the balanced equations for those, and then look at the equilibrium constants for each one of those reactions. And then you find the one that is the dominant one. And we're eventually going to end up with an ice table, right? So when we created ice tables in equilibrium chapter, that was not a futile exercise. We're going to use it again and again and again till the end of this course. All right. So these are just steps that you're familiar with solving equilibrium expressions, only they're applied specifically to acid-base reactions. So here's our first example. 0.80 molar solution of a weak acid, hydrocyanic acid. What are the major species? Right. Well, since it's a weak acid, the major species is HCN and water. All right. So why are hydrogen ions, cyanide ions, not major species? Because it's a weak acid. It doesn't produce many of them. Very, very small amounts. That's not a major species. So if we write the balanced equations for the reaction, we have HCN plus water yields hydronium ion plus cyanide ion, and the Ka for that reaction is 10 to the minus 10th. The reaction for water is 10 to the minus 14th, right? So which reaction dominates in producing hydrogen ions, hydronium ions in solution? The first one does. Right? Which one controls the pH? It's 4 orders of magnitude, well, actually 3.5 orders of magnitude, stronger. The hydrocyanic acid is that much stronger than water, so it controls the pH. That's as far as we took that count. We could go further with that calculation, but we're not going to. Now we're going to shift over into another weak acid, which is hydrofluoric acid. Now we want to calculate the pH of a 0.5 molar aqueous solution of weak acid HF. Again, major species, HF and water. Right. So there we have our balanced equations. We find that HF is the dominant reaction. Water can't compete with it. The controlling reaction is the dissociation of HF, even though it's a weak acid. All right. Now, what do we do with it? Well, what we have to do is find out what is the hydrogen ion concentration. So we set up an ice table. First, we put what is the initial concentration of HF? 0.5 molar. And since it's the controlling reaction, we can assume that hydrogen ion concentration is essentially 0 in the beginning. And that means the change is going to move the equilibrium to the right. That means we get, based upon our stoichiometry, we lose some HF and we gain the same amount of hydrogen ions and the same amount of fluoride ions. All right, so at equilibrium, we have 0.5 minus X in the denominator. And X times X in the numerator. And that's equal to our equilibrium. Oh, there's the Ka, that's right. 7.2 times 10 to the minus 10. No, 4, excuse me. I was thinking of hydrogen cyanide. There we go. And then we solve for X. Now, the problem is this could be, could end up a quadratic equation. What we have to ask ourselves is the X going to be significant? Is it going to be large? And since this is still 10 to the minus 4th, then the shift to X is going to be very small. All right, so what we can do is we can approximate. Oops. Defeats the purpose. There we go. Now we can solve it. We say 0.5 times this value, then take the square root of it. And we find out what X is. And as it turns out, X is the answer to our question, sort of. It gives us the hydrogen ion concentrations, and then we can calculate the pH. So X, once we multiply this times that and take the square root, we get 1.897 times 10 to the minus 2. We take the pH, do the pH calculation, and we get 1.72 is our pH. Let's see. Oh, this introduces the 5% rule, right? I gave that to you in the last chapter, remember? If you do this approximation, and then you plug that X value back in here, right? Plug that X value in here, here, and here, and calculate the K value from that value, then compare the two Ks. And if we do that, then we get 7.8481 times 10 to the minus 4th. Question is it within 5% of 7.2, which is the KW? I mean the Ka, excuse me. So how do you do that? Well, you subtract 7.2 from 7.481, divide by 7.2 times 100. And it's 3.9% away. It's within 5%. So our approximation was correct based on that rule. If the value had been greater than 5%, what would we do? Well, you have two choices. Either go back and leave that X there and do the quadratic, or take that X value that you just calculated, put it in right there, and leave these X. Solve it again. And then test your 5%. And I guarantee it will be closer. It'll be less than 1% difference. That's called the successive approximations. Okay. And if you have a computer to do it for you and set up to do it for you, then it's no big deal. For some equilibrium situations, we have a very complicated equilibrium expression, successive approximations may be your only answer. Like instead of a quadratic, suppose you have a cubic equation or a quartic equation, right? The quadratic solution is bad enough. You won't believe the cubic solution. Did you ever get introduced to the cubic solutions for a polynomial? Don't remember that? It's a massive equation. So if you go to power x to the third, x to the fourth, x to the fifth, then you're in stormy waters. So successive approximations for those types of problems is the way to go. Okay. Now let's talk about percent dissociation. So what kind of a value is pH? Is it an extensive property or an intensive property? Does the pH change? Once the pH is established, if you have the same concentrations of all the ions in solution and you have more of it, does it have the same pH? Yeah, it's an intensive property. pH is intensive. Percent dissociation is also an intensive property, but it approaches the problem from a different angle. Percent dissociation refers to the ionization of the acid. So what we're saying is that if we say the acid is 10% dissociated, that means that the amount that was dissociated from the original amount divided by the initial amount. Say you start off with a 1 molar solution of acetic C2H3O2. Percent dissociation has no meaning for strong acids, right? Because they're essentially 100% dissociated. But weak acids, if we say 1 molar and we say under these conditions, let's say just for argument's sake that it's 10% dissociated. What does that mean? That means 10% of that value, 0.1, divided by the original amount times 100. That's 10%. So we know that we've converted 1 molar there to 0.1 molar hydrogen ions. That's what that means. 10% dissociated means 10% of it ended up over here as hydrogen ions. Now, what we also notice is that for weak acids, the percent dissociation increases as the concentration decreases. Now, remember, this is an intensive property. So if we decrease the concentration to say 0.5 molar, this value over here, actually this value, it may be something like, I don't know, 8% dissociate, excuse me, the other direction, sorry. 12% dissociate. But what's 12% of 0.5? Well, I have to look at it. I have to calculate. 0.12 times 0.5, 0.06 gives you 0.06 molar hydrogen ions. Okay, so even though a decrease in concentration gives you a higher percent dissociation, the absolute amount, the extensive property of the amount of hydrogen ions still goes down. It's just that the percent dissociation goes up. That's counterintuitive, right? You would expect, well, if you didn't stop and think about it critically, then you would think that if this value is bigger than that value, then this value should be bigger than that value. But it's not, because of what we just calculated. this value may be larger than that value, but since this concentration starts lower, that value is going to be lower. All right. So I hope the next, let's see. All right, we're gonna go from that to something else. A solution. All right. We're using percent dissociation here to calculate the value of Ka for formic acid. Formic acid. Everybody know what formic acid is? You've been bitten by a fire ant? If you have, you know what formic acid is, because that's what they spit in the wound. Well, that's part of it. There are a bunch of others. It's a very complex mixture of chemicals, and they all cause blisters and extreme pain. Anybody ever lived in the deep South? West Virginia is not deep South. It's just barely South. Deep South, like Georgia, Alabama, and Florida, Mississippi, Louisiana. Right? If you've ever lived down there, then at some time in your life down there, you will step in a fire ant mound, and you'll know it. We used to work with, when I was in graduate school down there, and also research associate, we'd have graduate students coming in from the Midwest or from the Northeast, right? And we warn them, when we go out in the field, watch out for those big piles. They stand about this high. Don't get near those things, right? We warn them. It doesn't do any good, right? Sooner or later, they're doing something else and they step on that mound. And then there's the funny thing about fire ants. When you disturb their mound, they swarm up your legs, but they don't bite yet, right? There's one of them is carrying a bugle. When he blows that bugle, they all bite at once. And then the graduate student goes running across the field coming out of his pants. We haven't had any die from a shock reaction to it yet, but it is somebody. I've heard of people dying from fire ant bites. Anyway, and by the way, there are several species of fire ant, right? Several of them. A solution of 8 molar formic acid is 0.47% ionized in water. So its percent ionization is 0.47%. Doesn't seem like much. What's the Ka value? Well, we start off with 8 molar formic acid, right? And we're assuming that it is the controller of the pH, right? That its value is much greater than water. And we don't have any hydrogen or formate ion. By the way, formate comes from the Latin for ant. That's where it got its name. And what it's going to do is we're going to transition 0.47% into hydrogen ions and formate ions. So 0.47% of 8 is what we're losing in the change row. So 0.0047 is the decimal equivalent of 0.47%. I got that? Okay. So that's what we lose on the reactant side, and we end up with that much extra on the product side. And when you do the calculations, you get 7.9624 molar formic acid left in solution, and then the hydrogen ion and the formate ion concentrations are equal. Now that we know the equilibrium concentrations, we can calculate the K value, right? So we just put that in our equation. There it is. Plug it in your equation, and the Ka for formic acid under these conditions is 1.78 times 10 to the minus 4. Now, assuming the temperature stays constant, that K is a constant. Right? We calculated the K value. That value is constant no matter what the concentration is that we start. So let's decrease the concentration. Oops. Oh, they want to calculate the pH. Okay, so we take the Ka and we take the value of hydrogen ions and calculate the pH. So that's no big deal. 1.42. Now let's go decrease the concentration by half, 4 molar. Now, is the value of Ka going to be greater, lesser, or the same? That's a trick question. It's a constant, right? It's not going to change, right? So it's the same. How about the percent ionization? The percent ionization should go up, should increase, right? What is the percent ionization? That's what we're going to do next. Well, I thought we were. What am I doing here? Oh, I think this is an explanation why. Are we going to do the? Yeah, okay, we'll eventually do that. Okay, let me go back here. All right, we expect the percent ionization to increase as the concentration decreases. All right, so the explanation for that is coming up. So let's say we have a generic weak acid, HA. It starts off at HA 0, right? Sub-zero, that's the initial concentration. Right? There's what happens to it when it dissociates in water. There's our Ka value. And in this case, we're saying that HA is equal to the initial HA minus X, which, since it's a very small amount, is essentially HA. Now, what if we, oops, there we go. So the concentration of hydrogen ions and the conjugate base are essentially equal to X. Well, we set them equal to X. And the Ka for that reaction is going to be X times X over HA. Why? Because instead of HA minus X, it's just HA because X is so small. Remember that part? Okay, so that's our expression for Ka. What happens if we add water to this mixture so that HA becomes 1/10 as strong as it was before? Now, the new concentrations are actually X divided by 10. Which is the same as, and the concentration of HA is HA 0 divided by 10. Now that we've stressed the system, which way will the reaction move? Right? We calculate the Q. Right? Isn't that what you do when you stress the system? And you don't have, one side is not equal to 0 anymore. So you can't say it moves this way or that way. You have to calculate the Q and compare it to the K. So we've got the Q, and the Q, once we calculate the Q with these new values, then what we find out is the Q is 1/10 of K. So if the Q is less than K, what does that mean? It's less than K. That means the numerator is too small. Right? 1/10 K means the numerator is too small, the denominator is too big. So which way is it going to move? It's going to move to the right to make more numerator, to make more product. Right? And if we make more product, that means we've got to dissociate to a higher percentage the HA. That means that the percent dissociation increases. Correct? Does everybody see that? I don't have time to draw you a picture. We're running out of time. Okay, now we're going to take that previous example, go to 4 molar formic acid, and actually calculate the percent dissociation. We know that it's going to shift to the right. So if we start with 4 molar, then we're going to lose some X. We're going to gain some X on the product side. And we have 4 minus X in the denominator, x squared in the numerator. X is very small, so it drops out. And we calculate X now. What is the concentration of X? 2.665 times 10 to the minus 2. All right, so that's the hydrogen ion concentration, which is the amount of the formic acid that was dissociated. And we divide that by the original concentration, which should be on the next slide. Yeah, divide that by the original and times 100, and we have 0.67% dissociation. Right? Versus what? Did I put that in here? No, I didn't. So 0.67% dissociation versus what? Versus versus 0.47% dissociation. So it went from 0.47 to 0.67, I believe. Yes, it went from 0.47 to 0.67 by simply decreasing the concentration, cutting it in half. All right. So what's the pH of this 4 molar solution? Well, we just need the hydrogen ion concentration, the X value, and calculate it. And we get 1.57 instead of 1.27, was it? 42. 1.42 versus 1.57. So 1.42 pH at 8 molar versus 4 molar pH at 1.57. So the percent dissociation was 0.47, was it? 49, 47. Yeah, 47% versus 0.67% for this concentration. But the pH still went up, even though but it's not linear. Well, pH isn't linear anyway because it's a logarithmic scale. But the pH did increase with a decrease in formic acid concentration, as did the percent dissociation. So we can reason it, but in order to know the exact value, you have to run the ice table. You have to calculate it. All right. Bases. Right. We know bases in the Arrhenius definition. I said there were 3 definitions. I left out the third one. We'll eventually get to that one. But the Arrhenius base produces hydroxyl ions from the molecule itself, whereas Bronsted-Lowry's produce hydroxyls by reactions of the base with water molecules. And those bases are proton acceptors. Strong bases. In the chemical sense of the word, a strong base would be the alkali metals, hydroxyls, right? Lithium, sodium, potassium, hydroxyls. Those are all strong bases, and they're all completely soluble. The magnesium and calcium hydroxides produce strong bases, but there's a problem in solubility, right? Calcium and magnesium hydroxide is very slightly soluble in water. But by the chemical definition, whatever does go into solution completely dissociates. So they are strong bases by definition, even though they're not very soluble, right? I know that's a paradox. All right. So what's the pH of a 10 to the minus third molar solution of sodium hydroxide? Well, that value, let's look at it this way. The Ka, actually, the Ka of water is equal to the Kw, is 10 to the minus 14. Okay. So what's the Kb for water? Well, it equals Kw minus the Ka, divided by the Ka, which is 1. Right, 10 to the minus 14 divided by 10 to the minus 14 is 1. So the Kb would be what? It would be OH minus plus water. Right, because that's the base. And that's equal to water plus OH. Right, so that doesn't help you any, does it? Let's go back to the problem. Sodium hydroxide, 1 times 10 to the minus third molar, which is it's very much larger than 10 to the minus 14. So the pH controller is sodium hydroxide. Right? We calculate the pOH, then subtract it from 14, and we get pH of 11. So that's what we would have had to do for that example that I didn't like, the hydrochloric acid. That would have been, if we had added sodium hydroxide, then it would have given us hydrogen ions of a similar amount. Okay, calculate the pH of a 10 to the minus third molar solution of calcium hydroxide. In this case, we have to assume, right, for the moment, that all of the calcium hydroxide goes into solution. In which case, it would produce what concentration of hydroxyl ions? Well, if calcium hydroxide goes into solution, right, it's this. So it makes calcium plus 2 hydroxyls. So the stoichiometry dictates that the hydroxyl ion concentration is twice the molecular concentration. It'd be 2 times 10 to the minus 3 molar hydroxides. Right? So we do the pOH, subtract that from 14, and we get a pH of 11.3. All right. So the equilibrium expression for the conjugate bases use Kb. So we have the conjugate base of hydrocyanic acid is Cn minus, the cyanide ion. Right, and that Kb would be this expression. And how would we get that cyanide into solution? We'd have to pair it with some, usually an alkali metal, potassium, sodium, lithium. And it would completely dissociate and leave that cyanide ion, that strong base there, prepared to react with water. Okay. All right, that little box in there, sometimes it does that to me. When I've created the slides and then I try to show them on a different computer and the font's not there. So it throws that box in there instead of the double barbed arrow. What's the pH of a 2 molar solution of ammonia? And they've already given this Kb. All right. So we need, well, yeah, that's right. The Kb is based upon taking a proton from water. So if we throw this equation up, right, it makes these species minus Then we have initial change in equilibrium. Water doesn't count. Then what we have a 2 molar solution of ammonia. 2 molar ammonia. And we have nothing over here, nothing there. Then what's the change? Well, it's going that direction. So the stoichiometry says for every one of these lost, we're going to produce one of these. So we minus that one. So at equilibrium, we have 2 minus x, and we have x and x. That's where that expression comes from. X times x over 2 minus x. And we throw the x out because the KB, 1.8 times 10 to the minus 5 is so small. We can say that expression, then KB equals x squared over 2, which is equal to 1.8 times 10 to the minus 5. Then we can solve for x. And x is the hydroxyl ion concentration. We want to know the pH. So once we find the hydroxyl ion concentration, calculate the pOH, subtract it from 14, and we get 11.78 is the pH of a 2 molar ammonia solution. Okay. All right. So let's talk about what do acids do. Our example up to this point has only been monoprotic acids, right? HA. What happens when you have polyprotic acids, diprotic or triprotic acids? What happens is they dissociate 1 proton at a time. Let me give you a real world example. Try phosphoric acid. What's going to happen is there's an equilibrium set up with 1 proton dissociated, and then what's left over? Dihydrogen phosphate. And this is all aqueous. Okay? This has a K value. Ka1. That's for the first proton. Then you take this species here, H2PO4 minus, and it dissociates to lose 1 proton. And this is the abbreviated form. Remember, that proton is actually transferred to water. You never find protons floating around free in water. They're always combined with something. All right. So now we have HPO4 2 minus. So that's monohydrogen phosphate. That has a Ka also for that dissociation. Then we take the final one, PO4 2 minus, and it dissociates, giving up a proton and makes the phosphate ion. And that has a Ka also. Each one of those has a Ka. What we find is that the magnitude, the value of that Ka is greater than the Ka2, which is greater than the Ka3. And you can look at this logically for any polyprotic acid. This proton is being transferred from a neutral species, right? So it's leaving an electron behind and going over to water. But once you produce this ion, now you've got some coulombic attraction between that hydrogen that's trying to leave, that positive with this negative, and it's more difficult to get that transfer to go. And then you increase the charge even further, then there's more resistance to that proton leaving. That's why, whereas you have a certain amount over here, in this equilibrium expression, you have much less by percentage over here and much, much less over there. That's why the sequence is Ka1 is always larger than 2 or 3. Okay? And usually, the first dissociation step is the only one that's important to pH. Because typically, you'll see a difference between these two of 10 to the minus 4. And between these two of 10 to the minus 4. Right, 10,000 parts difference. There are probably some exceptions where these two could be close to each other. But in most cases, this one dominates the pH. So all you need to do is find the concentration of that one to give you the hydrogen ion concentration for calculating the pH of this solution. Now, these reactions still occur. They just don't influence the pH, but they will produce these species. Okay. Well, it's a good thing I chose phosphoric acid because there are your values. This is Ka1. Let's put it over here. Ka1 is 7.5 times 10 to the minus 3. So phosphoric acid is a weak acid. And then the second dissociation is about, actually it's 5 orders of magnitude difference. And the third one is 4.8 times 10 to the minus 13. All right, so I got that wrong. This is 5. This is 5. Okay. So there's the first expression based upon this, and this would be an abbreviated form. And if we have a 1 molar solution of phosphoric acid, this one's going to dominate. This reaction is going to dominate and produce the value for our pH. That's what we've calculated here. Now, the question is, we've got the hydrogen ion concentration at 0.0866. Is that within 5% of Ka1? No, it's not. 9.47%. So our assumption that X is small enough to ignore is incorrect. So what do we do? Well, we're going to use successive approximations. So what you do is you take that 0.0866 X and put it in that X that you eliminated the first time around. Then that value calculated gives you the new X of 8.27, and then you put that one in your expression and calculate the K, the Ka1, and compare that to the other one. And that's less than 0.5%, right? So the successive approximations in this case got us really close. And that was, in my mind, that's a whole lot easier than solving a quadratic equation. Okay. So what's the pH? Well, we take the second value of X, which is the hydrogen ion concentration, that gives us the more accurate value, and then we calculate that pH. And that's 1.08 for a 1 molar solution of phosphoric acid. Now, phosphoric acid is a weak acid. This proves it. But that's the intensive property. The extensive property is what's the concentration of hydrogen ions that can do damage, right? At this concentration, it might be an irritant, right? It will, right? pH 1, that's considered corrosive by EPA and OSHA rules. Anything less than 2, right? So it will be a corrosive to your skin. But the same concentration of sulfuric acid will do serious damage to your skin. However, if you have, you can get 100%, no, not 100%, 98%, I think, phosphoric acid. You can buy it, purify it in bottles. You know, it's that concentrated. If you stick your hand in that solution, it will eat it up right down to the bone. Actually, it'll beat the bones too. It'll form calcium phosphate out of your bones. But it's still a weak acid. But the concentration is enough to do the damage. Right? So there's a difference between what we consider weak acids and corrosives. Just a word of warning is all. So what's the equilibrium concentration of phosphate? We go through each one of these successive calculations to get down to this value. If you're starting with a 1 molar solution, right? Start with a 1 molar solution, then we do the ice table to find out what this concentration is, right? Then we take that concentration and do its successive to find out what this concentration is. And then we plug it into another ice table. And that gives us, that gives us concentration of phosphate at 10 to the minus 2 molar. So there's not very much there. Oh, excuse me, we haven't got there yet, sorry. 10 to the minus 19th molar. So it's there, there's just not much of it. All right. Now let's talk about acid-base reactions. And we're going to define the chemical definition for a salt. When you say salt, to most people, they think table salt, sodium chloride. But in chemistry, the salt is the product of, let me use a different one. Let's say KOH plus HNO3. Strong base, strong acid. This is acid-base reaction. We have hydrogen plus hydroxyl makes water. And then potassium plus nitrate makes potassium nitrate. All acid-base reactions produce these products, the water and the salt. That's the chemical definition of a salt. It's the double replacement reaction that combines the cation with the anion of the acid and the base. All right. Now, what happens if you combine two different salts? Right. What do you get, an acidic solution or basic solution? Well, it depends. The easiest approach is to take a strong acid and a strong base, and they will produce nothing but water and the salt. That means neutral pH. Right. You've got nothing but water in there. No excess hydrogens, no excess hydroxyls, because they've all been used up. These are completely soluble. In fact, this is soluble also. And then pure water. So the only reaction that produces any hydrogen ions is the same one that produces equal amounts of hydroxyls, which means the solution is neutral. So strong acid, strong bases produce neutral solutions. If, on the other hand, we have a strong base and a weak acid. Let's keep this strong base and let's use a weak acid like acetic acid, C2H3O2. Now you get K C2H3O2 plus water. Okay. But this is in solution. So it actually produces this plus this. Right? And what did we say about a weak acid? It produces a strong base. This is a strong base. So this further is going to react with that water. And what does it produce? It produces the acid plus hydroxyls. That means strong base, weak acid produces a basic solution. That's the chemistry. That's the chemical reason for this combination giving you a basic solution. The rule of thumb, which is easier to deal with, is whenever you combine a strong base with a weak acid, you get a basic solution. So the strong base says basic solution. But the chemistry says it's because of this strong base, not that strong base. Okay? And vice versa, if we have a strong acid and a weak base, then you get an acidic solution. Let's see. Okay. So the easy ones are strong acid, strong base, neutral solution, weak acid, strong base, basic solution, weak base, strong acid, acidic solution. The one that's up for grabs is weak acid, weak base. When you combine a weak acid and a weak base, what do you get? It depends on the comparison of the weak acid's Ka and the weak base's Kb. Which one is greater? Which one is bigger in magnitude? So if you combine a weak base with a weak acid and the Kb is larger than the Ka for the weak acid, you get a basic solution. Okay, there's our qualitative predictions. Right. Let's see. I'm not sure what I'm doing with this one. I lost my train there. And you'll notice that with the handouts, I gave you two separate problem sets. One for chapter 14, one chapter 15, with separate work problems. That's because when I started teaching this course in the beginning, I had 14 and 15 chapters separated and created those in advance. And later on, I said, I better put them together. So that's why you have two sets. Okay, calculate the Kb values for, I'm going to run out of time. For these species, this acetic acid and hydrocyanic acid. Right. So the Kb references the strong conjugate base. So we're actually calculating the K for acetate ion and the Kb for cyanide ion. Right. We know how to do that. We just divide the Ka into the Kw. There's the Kb for the acetate ion, and there's the Kb for the cyanide ion. And you'll notice that the Ka for the acetic acid is 10 to the minus 5, but the Kb is 10 to the minus 10. So where am I going with that? You're probably asking yourself. It should be a strong base. All right. Oh, the hydrocyanic acid is 10 to the minus 10th. Its cyanide ion is 10 to the minus 5. That is stronger. Yeah. Okay. We're going to run out of time. What we wanted to do was arrange these in 1 molar solutions of each of these compounds from lowest to highest pH. And we can do it qualitatively, or we can do it using their K values. Notice that some of them are acids, some of them are bases, and some of them are salts. So if we approach it qualitatively, we would say, are there any compounds composed of ions from strong acid, strong base interactions? Right? That would be right in the middle. That would be the neutral one. And we do find that sodium chloride is just such a compound, sodium hydroxide and hydrochloric acid. So that one's going to be neutral, right in the middle. So I give it a number 5. Why? Because they're 3, 6, 7, 8. They're 8 and 5 would be in the center. Are there any strong or moderately strong bases? Right, that would take care of the base end. Right, so we have ammonia. Sodium hydroxide will be the highest pH. Ammonia will be the next because they're pure bases. Okay, then we go to compounds composed of ions from weak acids and strong bases. That will give us basics. Right, we do have sodium cyanide will produce an alkaline solution with a pH that is a bit lower than ammonia. All right, so it's next. So maybe I should be putting these up here. So we've got sodium chloride in the middle, right? They went on the far basic end. Is that the order they want them in? From lowest to highest pH. Highest pH over here. So sodium hydroxide would be the highest. And then we would have ammonia. And then we would have sodium cyanide. Okay. There are any acids derived from halogens? Those are typically going to be strong acids except for HF. So the strongest acid in this case would be HBr, hydrobromic acid. Right? Lowest pH. And then HF should also be on this end. Right, so we got those two. Now we got to figure out what to do with ammonium chloride and HCN. So how we decide the relative positions of ammonium chloride, right? Ammonia is a weak base, and HCl is a strong acid, so it would be acidic solution. And hydrocyanic acid is an acid, but what's the difference? I mean, do we have the ammonium chloride here or the ammonium chloride there with the HCN? Well, the more basic should be the one that's a salt, ammonium chloride. And then this is a pure acid. It should be more acidic than that, even though this one has strong acid, weak base. That should be the arrangement. All right, so I should have them in that order. That, yeah. Now that's the semi-quantitative approach, the qualitative approach. Now, if we go at it from the comparison of Kas and Kbs, we find that if we put them in order of left to right, strong acid, then the next, 10 to the minus 4, 6.2, 10 to the minus 10, 5.6, 10 to the minus 10 is a more basic, then neutral, then sodium cyanide be 10 to the minus 5, and then this is a little bit stronger, and then the strong base. So using the Kas and the Kb comparisons, we can put them in order also. All right, if we have a 0.3 molar solution of sodium fluoride, the Ka for HF is 7.2 times 10 to the minus 4. First of all, what are the species, major species? Right. We find that sodium, right? This is sodium fluoride. This is a alkali salt of a halogen. It's going to be completely dissociated in water. So sodium and fluoride ions are there, plus water ions. Right? So we're going to get fluoride reacting with water. We're going to get water reacting with itself. This is a no-brainer. Sodium won't react with water. Sodium won't react with fluoride because it's completely soluble, right? Sodium won't react with fluoride. Yeah, that's right. So these two go out. We don't even consider them. Now we compare the number 1 and number 2. And in order to do that, which one controls the pH? Well, the fluoride is going to give us this. Fluoride plus water makes HF and OH minus. And then water with water makes that value. So we need to know the Kb for the fluoride reaction with water. That means we have to take its Ka and divide it into 10 to the minus 14. So that's 1.39 times 10 to the minus 11 is the Kb for that reaction. And compare that with the Kw, 10 to the minus 14th. The controlling reaction is going to be the fluoride. All right, that's as far as we're going with that one. We can do the same logic for hydrogen cyanide. A 0.75 molar aqueous solution of sodium cyanide. Then what are the major species? Well, sodium and cyanide ions, similar to the past one. Then we put up these possible reactions that could occur. We find out the sodium's not going to react with anything. So we're comparing the cyanide with the water again. We need a Kb for the cyanide to compare with water. And 10 to the minus 5th is much larger than 10 to the minus 14th. So the cyanide's going to win. And then we set up our ice table. We start off with 0.75 molar cyanide and no hydrogen cyanide, no hydroxyl, essentially. Then we set up our Kb value. Remember, this is Kb. This is not Ka. Kb is the cyanide plus water produces hydrogen cyanide plus hydroxyl. So we use the Kb here. And we're going to say, since that value is small, we're going to drop off that bottom X and say the X is 3.46 times 10 to the minus 3rd. That's the hydroxyl ion concentration. And we're going to assume for the moment that it meets the 5% rule. And that gives us a pH of 11.54. Okay. Now, there are 2 factors that control acidity in binary compounds. The bond polarity. The higher the bond polarity, the more acidic. What do we mean by that? Well, if you have H bonded to something over here, the polarity of the bond means this direction, right, toward the conjugate base side. And the larger this polarity, the more electron density you have over here, which means this becomes more positive to begin with, makes it easier to leave the molecule. So bond polarity, the strength of bond polarity increases acidity. Whereas the bond strength, the bond strength between HI, if it's a strong bond, you have well, actually, let's put it the way they did it. Low strength implies acidity. So the weaker that bond, the easier it is to remove the hydrogen. Those are 2 measurements that we can make of a hydrogen bond, a hydrogen bound to the rest of the molecule. Right. So here's an example. If we look at bond strength, right, we find that the bond strength, the bond strength of HI, HBr, and HCl they're relatively low as far as bonds go. And we find that once we cross that line between 427 and 565, we get that's a sufficient strength increase in bond that now HF is a weak acid and not a strong acid. Now, why does the bond decrease as you go down in the family? It's largely because the hydrogen, look at it this way, chloride, bromide, and iodide, the size of the atom by comparison. You got hydrogen out here, out here, out here. And the bond itself is more diffuse here than it is here. It's here. This strengthens the bond and it brings the hydrogen closer to the chloride than it does to the bromide or iodide. So this weakens the bond as you increase that size. And a weaker bond means a stronger acid. So hydroiodic acid is stronger than hydrobromic acid, which is stronger than hydrochloric acid. And is much, much stronger than hydrofluoric acid. Okay. Other factors that affect acidity. We're talking about oxyacids. Oxyacids are those typically with polyatomic ions, such as NO3 minus, SO4, 2 minus, C2H3O2 minus. If they've got an oxygen in them, they're oxyacids. Let's focus on the chlorides. Right. Remember the polyatomic ions, chlorate, chlorite, hypochlorite, and perchlorate. Okay. If we combine a proton with each one of those and make an acid out of it, what we find is that as you increase the number of oxygens in these molecules, you increase the acidity. So if we put chlorine in the middle, and we have possibility for one oxygen there, oxygen is more electronegative, and it adds to the electronegativity of the chloride, so it shifts electron density away from the hydrogen. If we add another oxygen, that increases the electronegativity of the group and weakens the bond even further with that hydrogen. And if we just keep adding oxygens, we increase the electronegativity of this group to such a point that now it's relatively easy for that hydrogen to leave for this one. So the acidity increases in that direction because of the number of oxygens. Okay. And you can see that in other sequences. This is the best one, I think, because it has 4 available oxygens in that homologous series. And here, this came straight out of your textbook. Right. So there you have the Ka values for hypochlorous acid, for chlorous acid, for chloric acid, and for perchloric acid. And you find that the Ka for this one is 10 to the minus 8, 10 to the minus 2, about 1, and then infinity for the perchloric acid. It's a very, very strong acid. So if we look at the electronegativity influence. So to do this, we need a homologous series, roughly homologous. So we look at these, let's see, HO, H, I. And then for fun, we put this one in here. That's methanol. It's just an alcohol. We find that as we increase the electronegativity, we should increase the acidity. And the same concept is true. If you increase the electronegativity, since the oxygens are the same for each one, then we're only focused on these right here, chloride, oops, bromide, and iodide. So the electronegativity increases as you go up, right? We learned that last semester. This increased electronegativity makes it easier for hydrogen to leave because the electron density has been shifted further to the right. So we find that the Ka for this acid is greater than the Ka for this one and greater than the Ka for this one, and much, much greater than the Ka for this one because the methyl group is essentially the same as carbon. HOF is not in there because we can't measure it. It decomposes. It's so reactive in water. It just decomposes into hydrofluoric acid and hydrogen peroxide. So we can't include it. Now, what happens when we have oxides? We're going to compare oxides of nonmetals versus oxides of metals. The type of reaction that is produced makes a difference in the outcome, what the pH of the solution is. Is it acidic or basic? Well, the example they're using here is sulfur dioxide. Right? Sulfur dioxide. So what does it do? Well, it's a gas, unless it's dissolved in water, of course, and then in solution, it undergoes the reaction that produces sulfurous acid. And you can show that for NO2 and CO2, right? CO2, right? There's a substantial amount of CO2 in the atmosphere, reacts with water and produces, oops, H2CO3, carbonic acid. So nonmetals reacting with water produce acidic solutions. Those are often called acid anhydrides. Whereas basic solutions are produced from metal oxides. Right? If you react this with water, what you get is KOH, which is an Arrhenius base. And any metal oxide will do that. Calcium oxide is another example they've given you there. Now here's the third definition of acid base. But what I like to do to make sense of this one is to go work from the Bronsted-Lowry, or let's see, Lowry. Sometimes it's this one. Lowry-Bronsted base, acid base, right? This would be HA plus water yields A minus plus H3O plus. What we've done here is transferred a proton to water. But if we look at it from a different angle, and by the way, G.N. Lewis was an American chemist who saw the need for expanding the definition of acid-base reactions because many of the reactions he was concerned with and other scientists were concerned with were not aqueous. So if it's not aqueous, you can't use that definition. But you can still apply acid-base theories using the Lewis definition of an acid base. So the Lewis definition, Lewis acid, look at what's happening here. When that hydrogen transfers to this water, what goes with it? Nothing, just the proton. Right? The proton goes and the electrons stay behind. So in this case, the hydrogen ion is donated to the water, but the electron pair is accepted by the acid. So if you donate a proton, you accept an electron pair. So that's the definition of a Lewis acid. Protons donated, electron pair accepted. That's a Lewis acid. And a Lewis base would be just the other way around. The electron pair is donated for a base. So if we had, say, BOH, and it would dissociate in this and this. So what happened here? Well, this is a base, and it donated electron pair, donated. It donated an electron pair to that hydroxyl so it could leave. That's the way I make sense of them. They're like the converse, right? Lowry Bronsted, hydrogen ions donated, electron pair accepted. And there are all three of them in the table for you. It's in your textbook. Organic chemists use this all the time because lots of the chemical reactions that organic chemists are interested in are non-aqueous. And they do that because if you conduct the reaction in water solution, the water is a reactant and it messes up your production. You don't get the product you expect. So many of the reactions in organic chemistry are carried out non-aqueous solutions. And with this definition, we're able to reason the outcome. Okay. I'm out of time. I got one more chapter to do. And if you have to leave, go ahead. What I'm going to do is finish the second chapter. Here we go. So I want to close this one. And open chapter 15. Okay.
You'll just put my score on.
In bright space, yeah. All right, so that was 14. Now we're going to do 15. Does everybody have to go? Okay, that's all right. I've lectured to an empty room before. In fact, I do it every Tuesday and Thursday. To my 100 class. Okay, let's make a slideshow. Here we go. Chapter 15. Chapter 15 is titled acid-base equilibrium, but we've already been working with acid-base equilibrium. What we haven't done is introduce the concept of the buffer. And that's where we're headed in this chapter. All right, there are two ways to shift an equilibrium by changing the concentration. You can change directly the reactant or the product concentration. We know that from Le Chatelier's principle. Or you can change those concentrations indirectly by coupling them with a second reaction. Right? We've seen that before. And what we need to accomplish this coupling is a common ion between the two, right? There has to be an ion that's present in both reactions that are coupled. Now, if we add an ion that's already involved in the equilibrium, then we can shift the equilibrium to its opposite side, whether that's product to reactant or reactant to product. But we have to identify the common ion. Now, in this reaction where we have hydrogen cyanide dissolved in water, and it's in equilibrium, that's a weak acid, and it's in equilibrium with the hydronium ion, of course, and the cyanide ion. And these are all aqueous. Of course, this one's liquid. Then what would happen if we added sodium cyanide to this solution? Well, if we add sodium cyanide, we know that sodium cyanide in aqueous solution is going to completely dissociate. Right? That means the common ion between these two is the cyanide. So if we add this to the solution, we're increasing the cyanide concentration and shifting the reaction back toward hydrogen cyanide. Now, what will that do to the pH? Well, it's got to consume hydroniums in order to move to the left, so that'll decrease the hydrogen ion concentration and increase the pH. It will become less acidic. What we're trying to do now is work into an understanding of what a buffered solution is and how it works. A buffered solution is one that simply resists the change in pH. Right? That's the most basic definition. Now, what do we mean by resists? We mean a buffered solution, if you add acid to it, the pH will become more acidic, but not much, just a tiny amount. There is a resistance to a change in that pH. That same solution, if you add a base to it, then it will resist the change toward the basic side. The pH will increase slightly, not much. It is resisting that change in pH. That is a buffered and an acid-base buffering solution. Most buffers are created by weak acids in combination with their conjugate bases. So if we had a concentration of hydrogen cyanide and its conjugate base, we could make a buffer. Or if we had acetic acid and acetate ion in the proper concentrations, we can make a buffer. All right. All right. I think we're getting a little bit ahead of ourselves here with this last statement. When you add a strong acid or a base to a buffered solution, you deal with the stoichiometry first. In other words, you say that if all of that acid or base added to my buffer is consumed, where will it end up? In concentrations. Then you use those concentrations as the starting point for an equilibrium calculation, an ICE table. All right. If you like flow diagrams. This is your cup of tea. I'm going to skip it though. What we're saying is, with these flow diagrams, we're saying what happens when you add a base or an acid to a buffered solution. And I like to draw, before we get to the Henderson-Hasselbalch equation, I like to draw a generic. So let's say we have an acid, and I'm going to simplify this. I'm going to use the abbreviated form. In equilibrium with its conjugate base plus hydrogen ions. Right? And this is a weak acid. And this is a strong base. Right? Strong conjugate base. And if you have enough of this one in there and enough of that one in there, actually the ideal is equal amounts. Equal amounts of that, and I'm going to prove it to you in just a minute. Then what happens if you add an acid? Well, if you add a strong acid, you're essentially adding hydrogen ions, right? There's your common ion. We're adding hydrogen ions by adding an acid. Well, if you add an acid, you're going to shift the reaction back that way, right? This is a strong base. It's going to pick up not all, but most of those hydrogen ions and shift back to this, the undissociated acid, right? That means that you're using up most of these hydrogen ions. And that means the pH will not shift very much. You can't use all of them up because this is an equilibrium, right? You'll shift the equilibrium position, but you won't shift the pH very much. You will have more hydrogen ions afterwards than you did before, but not much. You will have consumed some of this strong base. Okay, that's when you add an acid to a buffer. What if you add a base to a buffer? Strong base to a buffer like this, OH minus. Okay, what happens then? This OH, remember OH is formed from that, and that reaction is always there. So if this is a weak acid, this is a very strong base. Very strong. So it combines with that hydrogen ion. In preference to this one, right? Because this is attached to a water molecule. It's more readily available. And what happens then? Well, now the reaction shifts this way. It's consuming some of that hydroxyl. And when it does, it shifts the reaction this way and provides replacement hydrogen ions, but not much more. Only enough to reach equilibrium. Actually, there are two ways to look at this. That way, that reaction, or what would happen if these two react? Then that would produce what? Water, one hydrogen ion here, plus A minus. And it would shift to this side. But remember, this is a strong base. So this strong base is going to consume any extra hydrogens and reestablish equilibrium. So either way you look at it, this reaction is stabilized at a given pH, and it only changes very slightly. Remember, the other thing to think about is what is pH? pH is a logarithmic scale. Right? So you can change if the pH changes by plus or minus 1 unit, you changed it by either a 10th or 10 times. Right? So a fractional value of pH is not going to show up as a very large change. Actually, a small change in hydrogen ion concentration is not going to show up in a very large change in pH. That's the nature of the logarithmic scale. All right. Now I said usually you form a buffer with a weak acid and its conjugate base, but you can also form a buffer from a weak base and its conjugate acid. It's just the roles are reversed when you add an acid or a base. Most buffers are formed from weak acids and their conjugate bases. So that's why we come to the Henderson-Hasselbalch equation. HA and be in equilibrium with those two species. And I want you to be able to reproduce this logic. If you have to memorize it, fine. Ka then would be what? Well, it'd be H plus and A minus over HA. Okay? Now, let's say Henderson came first, chronologically speaking. And his work was done before Sorensen introduced the concept of pH. So Henderson solved the equation for hydrogen ions. He wanted to be able to calculate hydrogen ion concentration if he knew these other values. So this would be HA over A minus times Ka. Okay, or Ka first, either way. That was Henderson's equation in 1908. And then Sorensen came along a year later and introduced the pH system. So Hasselbalch took Henderson's equation and applied the Sorensen conversion to the whole equation. Okay, so if you take the log, the negative log of both sides, the negative log of this is negative log of hydrogen ion concentration equals negative log of Ka negative, excuse me. And then the negative log of this group. Okay. So remember, the log of A times B is the log of A plus the log of B. And since there's a negative in there, that's why you got a negative here instead. So we've done this one, pulled this one out here, pulled this one out here. Now, this is going to be pH, right? This is going to be pKa, right? And we're going to leave this one alone for just a second. Because the log of, we don't want to separate these out because of what we're going to do with it next. So this is still a negative log of HA over A minus. Except we don't like negatives. Right? So how do you get that negative out of there? Well, we use a rule from logarithms that the log of A over B equals negative the log of B over A. So if you flip these two, you change the sign. So now the equation becomes pKa plus the log of the conjugate base over the acid. And this is Henderson-Hasselbalch equation. And here it is in animated form. There you go. That's the derivation of the Henderson-Hasselbalch equation. So in order to find the pH of your solution, your buffered solution, all you need is to know the pKa of the weak acid, the Ka, and calculate the pKa. And then you need to know the ratio of the conjugate base to the undissociated acid. What we're saying also is that if the ratio is 1, well, actually, anytime the ratio is the same, no matter what the concentrations are, if the ratio of the two is the same, the pH of the solution will also be the same, because the log of that ratio is the same no matter what the numbers are, as long as they're the same quotient. Also, if you make this ratio equal to 1, right? If the concentration of A minus and HA are exactly the same, then that ratio is 1. And what's the log of 1? That's equal to 0. So this term becomes 0. And when this ratio is 1 to 1, then the pH is equal to the pKa. All right. So if we use the Henderson-Hasselbalch equation, and we know that in a buffered solution, 0.45 molar acetic acid and 0.85 molar acetate are combined. The reason we say acetate, sodium acetate, is because that supplies the A minus, right? The conjugate base. So if we set that equation up, then all we have to do is plug in the values for the conjugate base and the undissociated acid, calculate the pKa, and we find our pH is 5.02. This is your textbook artist rendition trying to explain what happens when the ratio changes. If the ratio changes between HA and A minus, then what we find is that adding hydrogen ions to this equilibrium situation removes some A minus. Well, what we're saying is the ratio doesn't change much. That's the effect of adding hydrogen ion. This is not a good explanation, I don't think. So now that we have the Henderson-Hasselbalch equation to work with, it's easier to understand how the buffered solution behaves. We need relatively large concentrations of weak acid and the conjugate base. In other words, if these values are large, then we have what's called a greater buffering capacity, right? Because that original equation, if you add acid and you only have a very little conjugate base, then it's going to be used up really quick. And when it's used up, it's no longer a buffer. So we want buffering capacity by increasing that concentration. And this just restates the fact that the pH of a buffered solution is determined by two things: the pKa of the weak acid and the ratio of conjugate base to weak acid.
concentrations. That will determine your pH. And here's an expression of the buffering capacity. It's just a way of saying how much acid or how much base can be added and still remain in the buffer zone, so to speak. And that can be calculated, right? This Greek letter beta is equal to, what we're expressing is when we change the N, or the normality of the acid or base added, how much does the pH change? You're not going to have to use this equation, so that's just for illustration purposes. All right. Let's see. Make some more room here. I've introduced the concept here called normality. Let me see if I got another slide after this. No. Okay. Normality is an expression, is a unit of measure that eliminates the need to know what acid or what base is being reacted. And here's why I say that. If we have a 1 molar solution of hydrochloric acid, it will produce 1 molar hydrogen ions plus 1 molar chloride ions. Okay? If we have a 1 molar sulfuric acid, it will produce 2 molar hydrogen ions and 1 molar sulfate. Now this is in a chemical reaction, right? And in a chemical reaction, we're not just dissociating the hydrogen ion from the sulfuric acid molecule. We're actually using up the hydrogen ions. So we're going to use up both of them, right? I remember earlier I said the first hydrogen ion leaves relatively easily, the second one not so easily. But when you're reacting this acid with a strong conjugate base, then it will take both of those protons. Okay? All right. So what we're saying now is that 1 molar sulfuric acid is actually 2 normal. All right. So if we know the normality of the solution is 2 normal, and this 1 is actually 1 normal, and we can react them with any base, and we only need to know the normality. Right? We don't care what the acid is. Now, if you're using this, if you're using acid-base reactions day in and day out, this normality is very useful. But if you're simply considering the stoichiometry of a chemical reaction, like we're going to do in about 3 weeks, then you can just write the stoichiometric reaction between acid and base and work from there. And when we get to that point in our laboratory exercises, I'll describe this in more detail. So how do we choose a buffer? Well, the best pH for a buffer is equal to the pKa of the weak acid. That's just a blanket statement, but now I want to prove it to you. And what we need
is to understand what a titration curve is for an acid and base. So let's say we have an acid here, right? That's our acid. Right? Our weak acid is in here. And then we have a burette filled with a strong base, sodium hydroxide. Right? And we can measure how much base we're adding to the acid, right? The pH will be less than 7 to start with. But as we add base, the pH will gradually increase. Okay? And we can measure that with our pH meter with increments of added base. So here's what it looks like. Right? Added base, say in milliliters, and then the pH. So since it's acid, it's going to start off here, right? At low pH. And it's first going to increase. And then it reaches a point where it kind of flattens out. That's your buffer zone. And then as we get closer to the equivalence point, where we've used up the acid, right? Now we don't have any of this left over for the equilibrium of our weak acid, as I described earlier. When we get to that point, now the pH is going to go rapidly higher, and then it'll reach a point where it levels out. Right here, that is the equivalence point. Okay? That's the equivalence point. When the added base in OH minus equals the acid in H plus. Right. Okay. Now, where is this point? Right in the middle of this buffer zone. Right here. That is 1/2 equivalence. Right? And 1/2 equivalence in terms of the Henderson-Hasselbalch equation is where half of this has been neutralized with base. And when half of this is neutralized with base, that means an equal amount exists on this side of the conjugate acid, the conjugate base of the acid. And at that point, this ratio is equal to 1. Okay? At 1/2 equivalence, that amount equals that amount, and this ratio is 1, which means the log of 1 is 0. That's why this pH is equal to the pKa. Okay? That's the best place. That's the ideal position for your buffer pH. It will move just a little bit. See? Notice it as you add more base, what happens to the pH? It doesn't move much. Doesn't move at all. Well, it does move some, but imperceptibly. Right? This is actually more realistic. See that buffer is not really flat, but it's a decreased slope.
So this is a representation of the pH curve for titrating strong base with a weak acid, acetic acid. Right? And Henderson-Hasselbalch tells us that 1/2 equivalence is right in the middle of the buffer zone. Right? pH equals pKa. Now, you can do it both ways, right? You could take a base, a little bit of base and add acid to it. And that way, no, excuse me, I'm getting ahead of myself. If you react a strong acid with a strong base, you don't get much of a buffer effect, right? This is actually exaggerated. That should be a very steep slope, and then steeper still when you get to the equivalence point. Strong acids do not make good buffers. Just keep that in mind. This one, and notice that the equivalence point is 7. Right? So when you put equal amounts of acid and base together, you get a pH 7, just like we mentioned earlier in our discussions. You can titrate the other direction, add acid to base, and you just invert the curve. Okay, so if we have a weak acid and a strong base titration, and we want to find out what's the end result of that titration at any point on that curve, what we need to do is first stoichiometry. Assume the reaction goes to completion and determine the concentration of the acid remaining in the conjugate base formed. Then you use the equilibrium problem. Sometimes we can use an ice table, or if we know we're at equilibrium, then we can use the Henderson-Hasselbalch equation and determine the pH. I think I've got examples. We're going to do it both ways. Okay. So say we have a solution of hydrocyanic acid, which we have determined to be a weak acid, and we add sodium hydroxide to it. We start off with 0.1 mole of HCN, and we add 0.04 mole of sodium hydroxide, and everything is in 1 liter aqueous solution. All right, so we can calculate the concentrations. First, major species. Right? HCN is a weak acid. Right? We have the hydroxyl ions and we have water. Right? There's the water reaction. There's the hydrogen cyanide in water. There's the hydrogen cyanide in hydroxyls. There's 2 equations that don't matter, right? They go out. Right? So we have to decide which ones do we use of 1, 2, or 3. Well, for the stoichiometry, we're going to use 3. Right? The stoichiometry tells us what reaction occurs before the equilibrium is established. Right? We have hydrogen cyanide plus hydroxyl, which is provided by sodium hydroxide. After this reaction, we have hydrogen cyanide still. All the hydroxyls used up. We have cyanide ions, we have water, and we have sodium ions. All right. Okay. So that was the initial stoichiometry approach for hydrogen cyanide and sodium hydroxide. Now we're going to go completely through with determining the pH for a reaction of acetic acid and sodium hydroxide under these conditions: 0.2 moles of acetic acid, 0.03 moles of sodium hydroxide in 1 liter of aqueous solution. So we have our major species, we have our equations, right? The stoichiometry is based upon the third reaction. Right, and there it is. Third reaction establishes stoichiometry. So we have 0.2 molar, right? We had 0.2 moles in a liter, so it's 0.2 molar. We're going to use up all the hydroxyl, and that leaves behind no hydroxyl and acetate ions and acetic acid molecules. All right, that's the stoichiometry. I guess initial change, ice table works. And this establishes the concentrations of the acid and the conjugate base. Then we can work another ice table where we're starting with, right, 0.7, 0.17, and 0.03 molar respectively. And we know that the reaction is going to proceed to the right because there are no hydronium ions. Right, so the change is going to lose some more acetic acid and gain some hydrogen ions and acetate ions. And that calculation then will give us a pH, eventually calculate a pH of 3.99. But suppose we know the values in advance, and instead we put them into the Henderson-Hasselbalch equation. The calculation then gives us 3.99 pH, right? Without so much trouble. All right. Let's say we have acetic acid, solution of acetic acid, and let's see, I'm covered up here. 100 milliliters of acetic acid. Oh, we're doing the pH of the purely acetic acid solution. Right. So we use the ice table and we find that it's 2.87. Remember, the Henderson-Hasselbalch equation only works if you have a conjugate base and the acid there together in solution. Otherwise, you can't use that equation. If it's just the pure acid, then you have to use the ice table. So let's say we calculate the pH of a solution made by 100 milliliters of 0.1 molar solution of acetic acid, which has a Ka of 10 to the minus 5 and 50 milliliters of 0.1 molar sodium hydroxide. Now we're creating a mixture that can work with Henderson-Hasselbalch. But first we have to do the stoichiometry. Let the reaction go to completion. Now we have these values. We have roughly equal acid and conjugate base. So I suspect that the pH is going to be equal to the pKa, or very close to it. Right? See, that value is almost 1, and the pH then is 4.74. That is an ideal buffer mixture. All right, here's another problem. What's the pH of a solution with 100 milliliters of 0.1 molar solution of ammonia, which is a weak base? And it has a Kb value of 1.8 times 10 to the minus 5 and 50 milliliters of 0.1 molar ammonium chloride solution. All right. Can we use Henderson-Hasselbalch? Well, if we can calculate the conjugate base and the acid, we have to determine what is the acid out of this equation. And the acid is not ammonia. The acid is ammonium. So that's where we're headed. We let the stoichiometry go. And the stoichiometry gives us, let's see. We're going to do an equilibrium, excuse me. Do an equilibrium. And solve that equation for, there we go. We're going to solve the equation for, let's see, Kb. Well, now I didn't create a buffer in this one, did I? Hold on a second. Oh, we're doing it the long way around first. Right? We know these concentrations, and we calculate and with an ice table what the values will be. Then we include those into the KB calculation, just as we've done before. And find out what X is, which is POH, and then we find out pH, okay? And external to this slide, we calculated for the 5% rule and found that it was satisfied. But if we use the Henderson-Hasselbalch equation, we know at equilibrium we have this arrangement. We have this much ammonium and this much base, conjugate base. See, we flipped the reaction. Now, it's not the former reaction, which is, let's see, ammonia plus water, ammonium. Now for Henderson-Hasselbalch, excuse me, we need to put the ammonium on the other side, reacting with water to produce ammonia. And we use the calculated concentrations. But what we need is the Ka, because Henderson-Hasselbalch doesn't work with Kb. So we calculate the Ka from the Kb of ammonia, and we find that value. Then we can plug that Ka into the equation, right? Plus the concentrations of the base and the acid. The acid's going to be on the bottom, conjugate base is on the top. And we find that the pH is 9.56, which is what we determined earlier. Okay, here's a slightly more complicated problem. What's the pH of a solution made by mixing 1 liter of 0.5 molar ammonia and with a Kb of 10 to the minus 5 and 0.5 liters of 0.1 molar ammonium chloride solution, and then add 0.1 mole of HCl gas. The reason we add it in gas form is so that we don't change the concentration. We're not going to add more solution. All right. What do we know? Well, we know the concentration of ammonia initially is, where the amount of ammonia is 0.5 moles. And the amount of ammonium is 0.1 moles. See, we're headed for stoichiometry first. So before the reaction, we have this amount of ammonia and this amount of hydrogen ions, which is 0.1 mole of HCl. So now we have ammonium. Well, we started off with 0.1 ammonium. Now we're going to lose 0.1 ammonia, and we're going to lose all of the hydrogen ions. And that leaves us with, I probably should have put a initial change and result, not equilibrium, but result. But this is where we're starting from, 0.4 moles of ammonia and 0.2 moles of ammonium. Now we go to the equilibrium situation. But we need to know the concentrations, and we need to know first the concentrations. We have added 1 liter of one solution and a half liter of the other one. So our total volume is 1.5 liters, and our total moles of ammonia is 0.4, so our concentration is 0.267. And by a similar calculation, ammonium is 0.133 molar. Now all we need is the Ka. Right, so we calculate the Ka, 9.25, which we did earlier, and use the Henderson-Hasselbalch equation and find that the pH is going to be 9.55. Now, one more. This is an important concept. Calculate the pH of the solution at equivalence point. The reason we want to do this will become obvious when we get to the point where we're discussing pH indicators, those that change colors at a given pH. We want the indicator to change color as near as possible to the equivalence point. So we need to know what that pH is. And this is the way you calculate it. So we have 100 milliliters of 0.1 molar acetic acid and 0.1 molar sodium hydroxide. And we know that the equivalence point is reached when the moles of acid equals the moles of base. The hydrogen ions plus the hydroxyl ions are equal. Well, acetic acid is monoprotic and sodium hydroxide is monohydroxyl. So we can use the molarity in this case, since the stoichiometry says for every one acetic acid, one hydroxyl. Okay. So what we need in addition to that is what's the total volume, right? Well, 100 milliliters of acetic acid at 0.1 molar is going to take 100 milliliters of sodium hydroxide at 0.1 molar because of the stoichiometry. So we know that the final volume is 200 milliliters or 0.2 liters. So before the reaction, concentrations of both is going to be 0.01 moles. If you have 0.1 liter times 0.1 molar, you get 0.01 moles divided by 2 liters, which is 0.05. Oops, excuse me, 0.2 liters, 0.05 molar for both. For both acetate and hydroxyl. Now we can put that into our stoichiometry. All right, so there's the stoichiometry. The concentration before the reaction is 0.05 molar for both acid and base. And when they react, we start off with no acetate. When they react, we use both of them up, right? This is equivalence point. So the acid must equal the base. And we lose all of our acid and base, and we produce the acetate ion. All right, so that's where we're starting, the acetate ion. Now, we have the reaction of the acetate ion. This is the equilibrium part. The acetate ion is reacting with water to produce acetic acid and hydroxyl. All right, so now we calculate the equilibrium to be 0.05 molar before, and then we're going to lose some acetate and gain some acetic acid and hydroxyl. But this reaction needs Kb. So we calculate the Kb using the Ka for acetic acid. Then we do our typical ice calculation and find that the OH concentration is 5.29 times 10 to the minus 6. We find out the POH and subtract that from 14, and the pH is 8.72. All right, now that we know the pH at which the equivalence is reached for this reaction, we can use that to determine where in the pH scale this occurs and which indicator to use. So that pH change is going to take place at what? 8.72. So if we look at 8.72 right in here, right? So what we need is an indicator that will change color at that pH. This illustrates the titration of a 0.1 molar acid with a 0.1 molar sodium hydroxide, and the shape of the curve and the equivalence point depends upon the Ka of the acid. So as the Ka gets larger, we move up this scale, right? And what was the Ka for acetic acid? It was 10 to the minus 8th, wasn't it? Right, so its equivalence point is going to be way up here, right in here somewhere. The other way goes with ammonia, right? Ammonia is a base, so we're going to add an acid to it, and the curve is inverted. Now, suppose what happens when you titrate a diprotic or a polyprotic acid? What happens is you get two buffer curves stacked on top of each other, right? The first hydrogen leaving under titration delivers a midpoint or a pH buffer ideal at this position right here, right? And for phosphoric acid, that occurs very near the first pKa, 2.16. The first equivalence occurs at about 4.8 pH. The second midpoint is the position of the second buffer zone, or the pKa2, which is 7.21. And then the second equivalence occurs at almost 10. And then the third hydrogen ion leaves at around the pH buffer zone of 12.3. That's the pKa3. And then the third equivalence occurs out here somewhere. Okay, so that's why many buffers in biological sciences use phosphoric acid as their weak acid, their base, because you can adjust the pH for the buffer and get either a buffer in the region of 2, in the region of 7, or the region of 12. So you have three options there. So the indicator, the acid-base indicator, is for convenience. If you do a titration curve for every sample you have, suppose you have 200 samples that have to be done in one day, you would not be able to produce a pH titration curve efficiently for that many samples in one day's time. So what we need is something that will indicate when we have reached the equivalence point by a color change. And that's what the indicator does. Now, they're not perfect, but if you get the pH change, the pKa of the indicator close to the equivalence point pH of your reaction, the error will not be significant. It will not be very large at all. This is phenolphthalein as our example. And we look at indicators as separate chemical reactions. We have an indicator which is in equilibrium with hydrogen ions and the conjugate base of the indicator. Now, when it's in this form for phenolphthalein, this is clear. So when would that be the case? Well, essentially when it's in basic solution, because if we don't have any hydrogen on this side and we have hydroxyls, then we're in basic solution. Or if we add enough hydroxyls to combine with these hydrogens and use them, most of them all up, we will be back over here, right? Shift the equilibrium that way. But if we're over here, that means we have a significant amount of hydrogen ions. And that means the equilibrium is to the right, and we have the pink color. Now, what's the pKa of phenolphthalein? 9.4. Okay. And there are the structures, right? You don't have to memorize those. That just indicates that there's a difference, right? A difference in the structure means a difference in color. Okay. So what we're saying is that for the most effective indicator, we want the pKa for the indicator to be in the region of the equivalence pH for our reaction. And it's a physiological fact that the human eye will detect a change in color for our indicator within plus or minus 1 unit of pH of the pKa. So if, what was it, 9.4? So phenolphthalein is pKa 9.4. So we can detect a color change if it goes, if it goes acid, it'll be 8.4. If it goes base, it'll be 10.4. Now that seems like a pretty wide range. So that's why when you titrate with these indicators, you have to be very careful when you get close to the equivalence point to watch and add drop at a time, because the slightest amount of change in added base will change the pH significantly in order for your eyeballs to detect it. So here we have a list. Now I know the print's kind of small, but this is available on the internet. It may even be in your book. This gives you a list of many of the pH indicators that can be used and the pH ranges in which they are most effective. And let's see, phenolphthalein is right down here, and it's most effective right around 9.4. Okay? Goes from clear to reddish. Of course, it's diluted, so it'll be pink. It'll look pink. If your equivalence point is different, right? If your equivalence point is, say, I don't know, in the range of 4.5, then you would use brome creasel green. And it would change between blue-green versus green-yellow, yellow-green. Some of these are easier to detect than others, the colors. So you have to also be careful with using an indicator based upon what you can see. The difference in color is more important. All right. So that's the end of the discussion of buffers. So work as many problems as you can. Next time we meet, a week from today, Monday, we will discuss the review problems. And then I'll try to squeeze in a little discussion about the titration reaction that we're going to use to determine the Ka of acetic acid.